So what we have here is that we always like start from say the root. So um, what you got to do is really compare this and this. So like whatever the value of like the root, you kind of like transfer it down. And right now you do operation z, where you start comparing the value. So you compare um, value, and before you compare value, I mean, of course you will have like you bring down the root value, downwards. Therefore you see 3 over here, and you start compare 3 and the value, and it will give you um, so at the end of the day, I think it just like biggest value will sort of like um, win. So 3 in this case will win. So therefore this is like not a good value. So what you do in W operation is that you bring the winner in, and in this case I mean it's like for 3. So you bring it over and you start doing this item again, and I mean 3 and 3 both are sort of like winners, so it's still considered that this guy can be an existing sort of winner, and then that's cool. And then you come over here, it's a 3 and then a 4. Cool. I'm not sure that like if there's like a bigger winner over here, do you bring it down here? But from my understanding is that you will bring the root over from here to here. So what's gonna actually happen is that this item is brought over. So it's like you bring the root, and then it's a 3, and then you compare the value, and which one is like a bigger winner. This item is also a bigger winner, so it's cool. And now like you always like bring the bigger winner over. So among these two is a 4, and you 4 compare, and which one is the winner. This 5 is obviously a winner as such. And you come look towards the root. You actually find a 3, and this 3 is also like a omega winner. Like it just feels like maybe the root, no matter what, will be a winner too. So, and then I mean at the end of the day, you just count how many winners are there. Like the core objective is to like really, I think ultimately count how many winners are out there. And so what we're gonna do is that like each time that there's like some form of winner, maybe I don't know, like maybe there's like an operation that actually records into the system of how many winner are there. So each time there's like a winner, we will record if there's like a maybe say a new winner, then we record. So here is one, here's one, here's one, here's one, like into the system on each where the node is. So it's gonna like come to here and say that like we have maybe say one like one is because we are considered the root, and then we're gonna plus whatever's on the left and whatever's on the right. So on the left there's like one of those, and on the right there's like two of those. So you want plus the each of the sides get. So obviously the left side there's like one, on the right side there's like two. So total you get like a total number of like 4 for the core objective. And I mean with that it's actually everything in terms of like the playoff series. So I mean the first item that comes to my mind is that it's like involving a form of like a lot of like multi operation like within a node. And there's some form of like memory storage in each operation. So like fundamentally you are constantly storing this data for your system, and whatever this bell is actually casting, it just reminds you a lot to do with DFS. So I mean you straight away like think of, wow, this looks really familiar. Like when you talk a lot about having like memory storage and to actually bring down to like the next value, you think a lot about like DFS. And I think like fundamentally it's just like at the core of like this whole playout series is that we are conducting this different operations within like nodes. So like there's always like some form of like existing new big winner over here and a new big winner over here, and obvious that like our big new winner will actually bring out to over here as well, which we actually missed, that eventually wins this. So therefore this is also not a winner. On a side note is that I'm gonna sidetrack here a little bit, is that saying that like if um, we choose a agenda, we are only able to actually speak about that agenda. If you say that like you suddenly talk about something else, you're gonna shift the agenda, you're gonna shift the space. If it's something that the person like doesn't actually resonate, so it's very important that when the person is speaking, you kind of like listen to the person, maybe you listen to her or what not have you, and that if you happen to actually jump in with a wrong set of words, you're gonna bring the whole conversation to a wrong set of um, agenda, and it's gonna like ruin the momentum of as such. Um, yeah. And I have some form of like predicted guess that on how that the items that's actually allowing the maneuver map to go like all the way down for one route. I feel like the mechanism that allows like maneuver map, it follows the maybe say there's like a standard formula of um, DFS that allows me to actually move from one place to the other, and same for here and same for here. So I've my theoretical guess is that there's like the formula of like using a DFS to allow it to like move around in this way. And I mean, in terms of like the Leetcode rulebook of what the requirement is that it just fundamentally wants you to actually count as many as possible for who the winner is. And by mean that winner, you are sort of like already doing the mechanism of like comparing values for each. And um, for this case, it's like comparing one value to the other. Um, and yeah, I think like fundamentally with this is that you are already actually able to actually build the whole entirety of the structure. And um, the character that we're sort of like introducing, it's really comes down to three, that it's like the core foundation of this whole problem. And when you talk about a character, a main character, you always use a brute force to actually fight against this main character. So for this case is that we have a problem like this one, is that what if say that I just like brute force my way through to actually count the values. and and the thing is this, that that if you were to brute force, you're gonna like calculate values like this one, and this one is just like a comparison of like maybe say this value with this and this. So it's gonna be inefficient in the sense that because you're gonna like need to have like an extra calculation. Like for this case, we have like an extra winner. Like we don't really want you to use this value to calculate for between this and this comparison, because in fact what you should be doing is this and this. And brute force, you are doing this extra step of comparing 3 and 5 when you just need to compare 4 and 5. So maybe say uh, operation n is like the comparison for 3 all the way down, and this extra move that you're doing, it's in under operation n, where operation L, it's comparing 4, which is the actual right one. So with operation n, you are giving this extra steps of comparison. And when you do think about operation E, which is like the actual tree comparison, where there is some form of like recognition of which one is like the bigger winner. As you dive down, you straight away know 4 is the bigger winner, and you're just going to use the right winner to actually compare it. In operation E, you can obviously tell that like if you were to use some form of memory to say which is the winner, you do less of this extra work that operation n produces. So with that, I use operation E as a form to actually argue against brute force. So with that, everything comes to an end.